Okay, so in our last video, we introduced this notion of a graph and its applications, how it can model lots and lots of real world scenarios. And we finally left off with this kind of abstract definition of a graph as a set of vertices or nodes and a set of edges. As a reminder, where each edge is a pair of nodes, saying that these two nodes are connected in this graph. So I wanted to start by talking about some properties that we can choose to define about our graphs that kind of change what they mean. So the first set of properties I want to talk about is this notion of a directed graph versus an undirected graph. So the big difference here is, what do we mean by an edge connecting A and B? So in a directed graph, we usually draw this picture as an arrow. So when we say there's an edge from A to B, we draw it as an arrow. Whoops, that's supposed to be a pen, not drawing text. There we go. We think of this as an arrow saying when A and B are connected, it goes from A to B. Now, on the other end, you could have an undirected graph where you simply say, well, if you have an edge A and B, there's no sense of direction there. They're just both connected, and we draw it as a line without an arrow. Depending on what real world or abstract phenomena you're trying to model, you can kind of choose, should you model it as a directed graph or an undirected graph? So for example, maybe in a social network, it makes sense to have an undirected notion if we're thinking about friendships on something like Facebook, because it's usually not the case that you can have one-way friendships where you're friends with someone on Facebook, but they're not friends back with you. So we usually think about these relationships as being bidirectional, or in another way of saying that, undirected, that there's no sense of direction there. But there are lots of contexts where graphs having direction makes sense. One common example that is used is prerequisites of courses. Usually we can model courses as a graph where each node is a course and each ed is a prerequisite from course A to course B. Prerequisites definitely have a directional attribute to them, right? Like CSE 143 is a prereq to CSE 373. So we would have an edge from 143 to 373, but it doesn't make sense to talk about 373 being a prereq for 143. It's not bidirectional or anything like that. So we would definitely want to model that as a directed graph. Now notice with direction, you can still have this kind of back and forth of having like A is followed by B, and maybe, for example, B could also be followed by A. The way we'd model this is having another edge where the arrow points the other way. So each edge can only kind of go one direction, but we can easily model this as just having an extra edge going from a different start point to a different end point. And this can be very common in certain applications where you kind of have these kind of bidirectional edges in some sense, but they're not, it's not anything special. It's just two separate edges. So directed and undirected is in some sense a design choice you have to make when modeling your situation. Which one makes more sense for my edges? The other property that we sometimes think about trying to choose in our model is whether or not we allow cycles in this graph. And a cycle would be something like the ability to go from one node and travel around and make your way back. So for example, down here, you can have an undirected cyclic graph here because you can go from A, go to B, go to D, go to C, and then go back to A. You have an undirected graph that has a cycle here because you can kind of start from one node and go back. It kind of forms a circle or a cycle. This graph above, this undirected graph, is acyclic because there's no cycle, because there's no way for you to kind of take a path, travel around this graph, and end back up at the same node you started at without repeating an edge you already used. So we don't really think about a cycle as being something where you can go like A, B, D, C, D, B, A. That's just like backtracking your steps. So we don't really think about that as like having some kind of loop that's closed. Now, this property of cyclicness or acyclicness also applies to directed graphs. So you can have a directed cyclic graph, but you have to be a bit careful here because you're only allowed to follow the direction of the edge. So here, this is a directed cyclic graph because you can go from A, follow this arrow that way, follow this arrow, follow this arrow, follow this arrow. However, if this graph were drawn differently, so instead of having an edge from C to A, we instead had our edge from A to C, this would no longer be a cyclic graph because you can't kind of go around the whole thing here. There's kind of a stopping point. So these notions of cyclicness also show up a lot. Why does it matter? Well, some algorithms will only work if you can guarantee that your graph isn't cyclic. Probably one of the most common ones that show up in a lot of places are these directed acyclic graphs. They actually show up so common that they have a common acronym. People call them DAGs. Directed acyclic graph. They just show up quite frequently in a lot of applications, so they get their special name. But it also makes sense to have an undirected acyclic graph or an undirected cyclic graph. They're just like different properties that we can use on this graph structure. Okay, so if I didn't mention this before, this video in particular is going to have just lots and lots of terms. These are all terms that you probably should write down somewhere, maybe make some flashcards. We're not going to like quiz you on like, oh, what is this term? What is the formal definition of that? No, we don't care about that. But a lot of times when we ask you to solve a problem, we'll say, suppose you had a directed acyclic graph, and we expect you to be able to know what those terms mean after you practice this. So kind of making sure you have these terms down, know what you mean, you can summarize them, explain them to someone else. That's a really good kind of starting point for this. Okay, next set of terms. We'd like to talk about graphs as having labeled and weighted graphs. So what I mean by that is you can usually, we usually think about letting you label the aspects of your graph, meaning that you can maybe give the vertex labels. So you could say like each node has a label associated to it, or alternatively, you can have edge labels where each edge has a label on it. You can also have both vertex and edge labels. The reason we just give, in some sense, this is actually kind of like, and somewhat unnecessary to add this kind of extra terminology, mostly because you probably want the ability to label these things. Like if you couldn't know which node was which, then what's the point of making a graph in the first place if you couldn't know how this node is different than this node? So it's very common that you just want to give things names, have these things store data. Now, it's very common that you will have vertex labels, so each node represents a thing with a name. It's sometimes common to have edge labels where each edge has some kind of thing associated with it. The most common type of edge label is that we'll see in our applications are numeric edge labels. So it's very, very common to have graphs where each edge has a number associated to it. And this will usually represent something like if you're thinking about modeling a physical map, like towns and roads between them, we usually think about these edge labels as being some type of cost or some type of travel time, and saying like the time to get from this place to this place is maybe the whatever number is on that edge. So we usually sometimes, instead of calling them edge labels, we sometimes call them edge weights. But we'll use that terminology kind of slightly differently later on. Now, 2 more terminology slides, and then I promise we're done. Next terminology. We have simple graphs, which are graphs that have no self-loops or parallel edges. A self-loop is a graph that has a node that has, turn my pen on, has a node that has an edge to itself. That's technically allowed in our definition. Right? You could just have an edge that has the node twice for both entries. You could also, as I shown you before, to kind of create this idea of a bidirectional thing, you can have what we call parallel edges, where in a directional graph, A points to B and then B points to A. Now, these are all well and good and maybe do have real life applications, but they generally complicate a lot of the algorithms that we're talking about in this course. So we think of a simple graph as being one without self-loops or parallel edges. And when we talk about this, one of the reasons is it helps us make statements about how many edges are going to be in this graph in a very succinct way. We say that the number of edges in a simple graph is going to be big O of V squared. Now, why is that? Big O of V squared is kind of saying essentially the densest graph, or the graph with the most edges, is kind of this fully connected graph where every node is connected to every other node. And so that's kind of the maximum. It's O of V squared. And so it's going to be upper bounded by that. Now, unless otherwise stated, we are always going to assume graphs in our course are simple because they kind of usually mess up our analysis or they mess up kind of our algorithms. So unless we state otherwise, you can assume it's simple, no self loops, no parallel edges. One other term we use is this idea of adjacent vertices. So if a vertex has an edge to another vertex, then we call them adjacent. They're neighbors is another term we sometimes use for them. And I mentioned before that the vertices or the edges can have labels, which is totally allowed. Oh, I promise, only one more slide of terminology that we're going to introduce in terms of like definitional things. I have to close my drawing app. Okay, now the last two terms I'm going to really introduce are these things called connectedness and path, and we'll also talk about this thing called degree. So two vertices are connected if there is a path between them. So if you look at this graph up here, the vertices F and G are connected because there is a series of edges you can take to get you from F to G. However, F and J are not connected because there is no path. There's no series of edges that get you from F to J. So we can think about two nodes being connected, but we can also think about the graph being connected. The graph is connected if all pairs, if all vertices are connected, meaning you could reach one vertex from any other vertex. Then we call it, if that's true, the entire graph is connected. Now, thinking about kind of connected graphs, we usually like to think about this idea of the degree of a node. So the node has a degree of the number of edges leaving it. So for example, you can have in this graph up here, F has degree 1 because there's one edge leaving it. You could sometimes qualify this as what is the in degree versus the out degree. In degree being how many edges are coming into this node, out degree being the number of edges coming out of the node. For undirected graphs, you can only really talk about the degree because there's no in or out of relationship in undirectional graphs, or undirected graphs, sorry. And in directed graphs, it sometimes makes sense to differentiate between in and out. I kind of already used this term path, but a path is a sequence of vertices connected by edges. So you could take a path, like a stroll through this graph, from one town to the next along the roads, and the path is the series of roads you took along the way. A simple path is a path that doesn't repeat any vertices. So it's one that doesn't kind of like visit the same node over and over again, kind of along the way. And I already kind of used this term cycle, and it's a path whose first and last vertices are the same. So for example, you can have a path here from P to I, let's just delete that, from P to I to M, from M to P. That is a simple path that formed a cycle. And similarly, we talked about kind of earlier with directed graphs, you can really only follow the direction. So this graph does not have a cycle because there's no way of you following these directions to end back at where you started. And just like with this connected property, if a cycle exists, we call it a cyclic graph. So that we can make global statements about a graph if we know kind of part of its structure. Oh my goodness. Okay, we did all of our terminology. Lots of terms there that we will use pretty commonly, and so they're all good to know. But again, we're not going to quiz you on kind of what these terms mean. We just kind of we expect you to kind of be able to reason about what these things mean when we kind of tell you about inputs for your problem. What I want us to do for the rest of this video is I want us to actually kind of practice all of these terms that we just used and try to model some situations with a graph. So what I'm going to have you do to start with, I have a couple scenarios here, and I want you to describe to me what would we use in each of these scenarios as the vertices and what would we use as the edges. So for each one of these, it's just going to be one big free response box. But for each one of these, what are the vertices in the scenario? What are the edges? Take a second and think about that. Okay, let's go ahead and talk about this. So for web pages, a very common way of representing this would be the vertices themselves would be the individual web pages. So you have one web page, like my homepage on my course website, and then edges would be links. So if there's a link from page A to page B, we would have an edge there. And since there's kind of this directionality, oops, sorry, I didn't mean to hit my microphone. Hopefully that wasn't too loud. If there's this directionality between linking, like just because I link to a website doesn't mean that website has to link back to me. This is probably a case where we want a directed graph, one that has this directionality between them. If you're thinking about ways to walk between the UW building, well, maybe UW buildings, maybe the vertices would be something like buildings, and edges from, oh, I have a typo here. I think I changed my example. That old one is about family trees, so ignore that. Buildings aren't getting married or having children, I hope. But edges are kind of matching roads, saying that there's a path from this building to that building. And it's undirected since each route can usually be walked both ways. There's very few routes at UW that you probably are actually unidirectional, so it probably makes sense to model it as an undirected graph, just assuming all paths are undirected. Think about course prerequisites. The vertices could be courses, and the edges could be an edge from A to B if A is a prereq for B. And so in this case, it would be a directed graph because prereqs kind of flow one way. Okay, let's try one more example together. Let's think about the Paris metro. Let's try formulating as a graph. What set of characteristics kind of makes sense here for our graph modeling of this scenario? So take a second. What do you think the set of properties will want of this graph? Okay, so I hope you had some time to think about that. In some sense, there's no right answer. Why? Well, how you choose to model something depends on how you want to use it. What problem are you trying to solve by modeling the Paris metro? It really depends. There are some properties that are probably pretty easy to pin down, or at least kind of no matter your context, probably makes sense to apply here. So for example, in the Paris metro, getting from one station to another tends to be an undirected process because a train that goes one way can always go back. That's usually how these subways work for the most part. It's usually the case that you can't go from one part of town to another and then have no hope of getting back. So we'll probably think about these things as being, whoops, my pen didn't show up. As being, oh, my pen is just done for good. Okay, well, there's no pen. Oh, and now the slides are closing. We'll just quit that entirely. So we'll probably think about this being as undirected, that there's no direction between these things because any station in the metro can go either way. Now, we probably want this graph to be connected. We probably don't want some part of Paris that's completely isolated from everywhere else. It's probably going to be cyclic too, and you can see that just from maybe a picture of this, that you can usually always kind of go around, go from one place to another and always make your way back. There's usually at least one place, at least kind of in maybe the busiest part of the city, where you can kind of get to one place from multiple directions. And then the question is, do we want labels? And if so, where? This is really a design choice for your context. It usually makes sense to have vertex labels for something like this is the station name. But it also might make sense to have edge labels, like this is the name of the route that you're taking or the street that this subway goes under, or maybe the time it takes you to go from this station to another. Maybe you don't care about that stuff at all. Maybe you don't need labels at all. You just want to plot a pretty picture of the Paris metro. You don't need any of those labels. So it really depends on what your context is, what you're trying to solve here. Now, in our next video, and we're going to be introducing, okay, I maybe have been getting this idea of the graph, but how do I actually represent this in code? What data structures do I use to actually represent this? And then afterwards, we're going to kind of do some setup for what we're going to be talking about for the rest of the week with graph algorithms.